This week we're going to work with specific heat and reactions. We've done enthalpy and I hinted at specific heat, but this week now we get to see it in motion. And the first thing that I want to focus on, because it's going to help you with deciding what energy is involved in some sort of specific heat interaction. And one of the most common things you'll see is these heating curves. And all these heating curves tell you is what's happening here, going from here to here. So this would be, let's say I have a nice slope here. I'm increasing temperature, and while I'm adding energy, and then I have this flat section here where I'm just adding energy, but nothing is happening to my temperature. What's happening from here to here, well, this is a phase change. Let's go ahead and write that down. This is a phase change. Phase change. And that phase change is happening at that plateau and that plateau. This area here then would be when I have something that is a solid. I need another color. So this is going to be my solid phase. This is going to be my transition from my solid to my liquid. So here is my liquid phase. And then I'm adding energy, increasing temperature until I get here. My temperature remains the same, and now I'm just putting all that energy in to make this phase change go from a liquid to a gas. So this is a phase change, and this is a phase change. For water, this is happening at 100 degrees C. I'm sorry, 0 degrees C. And this would be happening at 100 degrees C. So it's pretty cool, because if I have a bucket of ice, because everybody gets a bucket of ice and then tries to melt it, why not? So we have our bucket of ice, and I'm going to start heating it. And as I start heating it, I'll see like the ice not doing anything terribly exciting, but my thermometer will record an increase in temperature. And then all of a sudden, I'll stop seeing, I'm still adding this energy in, but I'll stop seeing this increase in temperature, and it's all that energy is going in here. So all the energy that's being entered in here is breaking those intermolecular forces. And what's fun to keep note of is that I have ice at 0 degrees C, and I have water at 0 degrees C. I can have both. And more importantly, that as we start doing math with it, if I have a phase change, there's a certain amount of energy involved in this phase change that doesn't have a change in temperature. So I come here, I'm a liquid at 0 degrees C. So I start at 0 degrees C, I start adding heat to it, heat, energy. I get to my plateau, I'm like, oh, look, that plateau is a lot longer than this one. So it tells me, looking at this heating curve, that this interaction from my liquid to my gas, I'm having to break some really strong intermolecular forces here, or actually less energetic intermolecular forces there than I have here. Another way to think of it is that, especially from our water, we have all those happy hydrogen bonds going on in water, and now I'm going to turn it into gas and make it go play all by itself when it really likes its friends. So I'm going to break all of those intermolecular forces. That requires more energy. And then it goes off into its gas. So my gas phase starts at 100 degrees and then goes up to however high I want to make it. And the reverse then would be true. If I start off with a gas and I see the temperature is decreasing, then that means the system is losing energy. So this would represent like condensation. You get in the hot shower, you're enjoying your nice steamy shower on a not today day, and you see all the gas just kind of hanging out in the bathroom, and then all of a sudden you see it kind of starting to condense. Well, as it's condensing, it's releasing energy into the surroundings. So that continues to happen. Now we're going into our phase change. More and more energy is released until we get to here. Now we have all of my gas has gone into the liquid, and it continues to release that energy, goes into another phase change, So here I'll see a change in temperature, and here I'll see a change in temperature, and here I'll see a change in temperature, but not here and not here. Cool. So this one, keep in mind for when we do math on the next video. The one you're going to see in lab this week looks something more like this. It's a little bit bigger. I don't know why I made that so high. This will be like in temperature in degrees C. And then over here it's going to be like time. And what you're going to do, it's so sad that you're not going to get to do this. This is so much fun. What you would do in real life is you have these little syringes with precisely measured amounts, and you're going to add some ethylene diamine to some solution, and you're going to watch temperature changes happen in real life. So you'll have a thermometer that's hooked up to the computer, and that thermometer tells you increases in temperature. So I would have this displayed, temperature versus time. And then I would start, just hit record, and I'd start seeing something like this, where, at first it's going to kind of, different color. Let's do a different color. First you'll kind of see this little bit of increase while your thermometer is just coming to thermal equilibrium with the solution. And then all of a sudden it'll get kind of plateauy. In real life, we tell you to reset everything so you don't accidentally lose a lot of your data, and you'd start your whole collection over once you have this plateau. This just means that your thermometer is in thermal equilibrium with the solution. That's all it means. So this is going to be when the fun starts. So you get this little piece here, and then you'll have you or your partner adds some of your ethylene diamine in, and then all of a sudden you'll see this spike. Like it just blows up. It's kind of fun. And it's just this instant increase in temperature in the solution. So what I'm challenging you there is, if the solution is increasing in temperature, what does that tell you about the reaction that's happening inside? Is that endothermic or exothermic? Cool. Now, unlike this, all of a sudden you'll start seeing it kind of go like this, where you get this almost plateauing. At first it'll be a little bit difficult to tell, but you'll definitely know you've gone too far if all of a sudden you see it decreasing. So what's happening here is we're creating what we call a closed system, but it's still a styrofoam cup. So after my reaction has happened, if I do it fast enough, it behaves like a closed system. If I go too slow, what's happening here is that I'm now interacting with the environment. I don't actually have a closed system. My styrofoam cup isn't all that high-techy after all. So that's all you're seeing there, is it's starting to come to room temperature. So ideally we'd be around to say, no, add in your ethylene diamine now, and you would add in more, and then you see this another curve, a little spiky, temperature goes up, and then the same pattern happens. So every time you would add a syringe of ethylene diamine, this means that you have some kind of mole reaction happening with that addition of the ethylene diamine. So I'd have some equivalence amount. I'm using up one of my reagents in my styrofoam cup and all of my ethylene diamine. Cool. If it happens again when I add another syringe full of ethylene diamine, that means that I still haven't used up all the reagent that's in the cup. So I have still done another step in a chemical reaction. So here, what we're trying to figure out is just how many ethylene diamines can I get onto one of my nickels. I totally forgot what the reagent was, sorry. So we're going to add that on, and we want to know how many will fit. That's the point of the reaction. And eventually, in real life, you'll get to where you're like, you'll do an addition, and you'll get excited. You're like, oh, I had an increase, and then it goes like this. And then you realize, well, that's just like a carryover of you didn't actually use all of your solution. But you only had, this is starting at neutral, so your starting point. So I'd have one addition of ethylene diamine, two additions of ethylene diamine. And if I saw this, that means I didn't have another addition of it. So I just have two. And what I want to remind you of is ethylene diamine. We do this like little hooky thingy. And that means that I have two places, two bonds, two nitrogens that are going to interact with my metal center per ethylene diamine. Important thing to remember. Okay, so that's our heating curves. It's a little hinty hint for your ethylene diamine addition, and we will move on to doing some math next.